From the previous videos, we realized that we can use the following steps to solve a system of linear equations systematically, and this process is called Gaussian elimination. It can be described as follows. We first reduce the augmented matrix of the system to row echelon form using elementary row operations. From the last video, we have proved that we can reduce any matrix to row echelon form, so we know that it is always possible to carry out this step. The second step is that if we see that the last row is a zero row except the last entry is a 1, then the system is inconsistent. Otherwise, we can solve the system by backward substitution and assign the free variables as parameters whenever they appear. Now, let's see some examples of how we can solve systems of linear equations using Gaussian elimination. As usual, we first write the system in the form of an augmented matrix. We observe that all entries in the first column are 1, so the first step that we have to do is to subtract row 1 from all the other rows. So we replace row 2 by row 2 minus row 1, and replace row 3 by row 3 minus row 1, and replace row 4 by row 4 minus row 1. The augmented matrix becomes this. Next, we observe that the second row has a 0 in the second entry and even in the third entry. But we cannot leave it like that because we see that the leading entries in the third row and the fourth row are in the second column, which are not to the right of the leading entry in the second row. So the matrix that we obtain would not be in row echelon form. So what we should do is to move either the third row or the fourth row to the second row. And we prefer to move the third row because the leading entry of the third row is 1, but the leading entry of the fourth row is -1. So we swap row 2 and row 3 and get the following augmented matrix. Now, we will change all the leading entries below the leading one in the second row to 0, and since the second entry in the third row is already 0, we just have to make the leading entry in the fourth row to 0, and we can do that by replacing the fourth row by the fourth row plus the second row. And since the third row remains unchanged, we can multiply the third row by 1/3 to change the leading entry to 1. And we obtain the augmented matrix in row echelon form. Now we convert the rows of the augmented matrix back to equations and solve the system. As we have seen before, we ignore the 0 row and start from the third row. It states that x4 plus x5 equals 0, so we set x5 equals a to get x4 plus a equals 0, which means that x4 equals -a. Now the second row is x2 plus x3 plus 3x4 plus 2x5 equals -1. We already have x4 and x5 in terms of a, and we have to find x2 and x3. So we set x3 as a parameter, say b, and get x2 plus b plus 3 times -a plus 2a equals -1. So we have x2 equals a minus b minus 1. Lastly, the first row is x1 plus 3x3 plus 2x4 plus 5x5 equals 1. By substituting the expressions for x3, x4, and x5, we get x1 plus 3b plus 2 times -a plus 5a equals 1. So we have x1 equals -3a minus 3b plus 1. So the general solution is -3a minus 3b plus 1, comma, a minus b minus 1, comma, b, comma, -a, comma, a, where a and b are real numbers. Let's look at one more example. The augmented matrix of this system is this. To begin, we observe that the leading entry in the first row is 3, and we want it to be 1, but it is not ideal to divide the row by 3 because it would create fractions in the other entries of that row. Luckily, we can avoid this situation because we observe that the leading entries in the third or the fourth row is 1, so we can swap one of them with the first row. So let's say I swap row 1 and row 3. we get this augmented matrix. Now we change all the entries below the leading one to 0. Depending on the leading entries of the rows, we subtract different multiples of the first row from the other rows. For row 2, the leading entry is 2, so we subtract 2 times row 1 from row 2. The leading entry of row 3 is 3, so we subtract 3 times row 1 from row 3. The leading entry in row 4 is 1, so we subtract 1 times row 1 from row 4. We get this augmented matrix. Next, we observe that the leading entry in the second row is 7. And again, we try not to divide the row by 7 directly, because we don't want to create fractions in the later entries in that row. So we look at the entries below the 7, and luckily, we see that those entries are all multiples of 7. So we can subtract appropriate multiples of the second row from the third and the last row to create zeros below the leading entry in the second row. We can do so by replacing row 3 by row 3 minus 2 times row 2, and replace row 4 by row 4 minus row 2. We get this augmented matrix. Now we observe that the last row becomes a 0 row, so we would get the matrix in row echelon form if we divide the second row by 7 and divide the third row by 6. However, if we are just interested in solving the system, it is not necessary to do this step because the leading entries corresponds to the coefficients of the variables that we want to solve, and it would be enough to divide that coefficient when we solve the equations one by one. Ignoring the 0 row, the third row means that 6x3 equals 0, so we divide 6 to get x3 equals 0. The second row states that 7x2 minus 3x3 minus 22x4 equals 1. And since x3 equals 0, we just need to set x4 equals a to get 7x2 minus 22a equals 1. So x2 equals 22a plus 1 divided by 7. Notice that it is inevitable that we have a fraction for the expression of x2, but it would be better than having a fraction in the augmented matrix, because the numbers are already quite packed there. Lastly, the first row gives x1 minus 2x2 plus x3 plus 10x4 equals 0. So we substitute the expressions for x2, x3, and x4 to get x1 minus 2 times bracket 22a plus 1 over 7 plus 0 plus 10a equals 0. So we have x1 equals 2 minus 26a over 7. Therefore, the general solution is 2 minus 26a over 7, 22a plus 1 over 7, 0, a, where a is a real number.